All right, ladies and gentlemen, so we are going to pick up with chapter 4 today, and this is really going to be a general introduction to organic chemistry, looking at carbon and how carbon has sort of become the backbone to all of the living molecules that we see here on Earth. So, if we're talking organic compounds, let's make sure we understand what that means. So, all living things are made up of chemicals, and the vast majority of those chemicals are based on carbon as being this centralized atom, centralized element to the vast majority of those compounds. So remember your carbon cycle, right? Carbon's going to enter the biosphere via photosynthesis by creating carbon dioxide into glucose, and then we sort of wrap that up the food chain, and the animals eat those producers. Those animals then go through cellular respiration to turn that glucose back into carbon dioxide, and the cycle kind of continues from there. When we talk about organic compounds, we're really talking about carbon-based molecules. And the true definition of an organic compound not only is that it contains carbon, but that it also contains hydrogen. So anything that would be considered organic must contain carbon plus hydrogen. So technically speaking, carbon dioxide actually isn't considered an organic compound, even though it is essential to life. So sort of just keep that in the back of your head. Water, same deal. It's H2O, hydrogen and oxygen. Um, Once again, very much essential to living things, but technically not an organic compound. Um, when we look at a lot of the other chemicals that are carbon-based in living things, they often are a combination of carbon plus other elements that are essential to life, so carbon and the hydrogen, but often also oxygen, nitrogen, sulfur, and phosphorus also become players as elements in organic molecules as well. So again, organic chemistry really is the study of those carbon-based compounds, specifically the carbon plus the hydrogen. So go all the way back to understanding, if we're looking at this from a biological standpoint, we're looking at how did this stuff get here, right? So how did these molecules become what they are and their significance to life as we know it now? And go back to evolution and remember that Miller-Urey experiment where they were looking at that operant Haldane hypothesis, that idea that these organic compounds could have become formed given what the conditions and molecules were present on early Earth, things like the water, the ammonia, the methane, um, and then take into the account the hydrogen gas in the atmosphere, the potential energy coming from lightning, and we were able to, at least they were able to in their lab experiments, be able to create basic monomers, basic building blocks for organic compounds like such as amino acids. And so their experiment really sort of set the stage for the origin of life and tying that connection of organic chemistry to living things as a way to say this is how at least the chemistry of life could have gotten started. So if we're talking carbon-based chemistry, then we probably should have a basic understanding of the structure of what carbon looks like. So when we look at carbon in terms of doing some sort of like Lewis dot structure or electron diagram, we look here. Carbon has a total of 6 electrons, 2 in its first orbital, and then the ones that we're really particularly interested in are the 4 valent electrons in its second orbital. So we talk about carbon being tetravalent, tetra meaning 4, so 4 valent electrons. And based on carbon's electronegativity and those 4 valent electrons, carbon participates in covalent bonding. And so it is able to make up to 4 covalent bonds, which is going to really set the stage for its diversity in being able to build all sorts of different kinds of molecules. If we take a look at the periodic table, technically speaking, anything within that 4 valence group could have potentially become an option as a building block for living things. So if you ever hear, especially in like old sci-fi movies and shows where they talk about carbon-based life forms, we are carbon-based life forms. Why? Because we've got those 4 valence electrons. That's going to provide carbon a great ability to produce large, diverse sets of molecules. And so we believe that's the rationale or the reasoning behind our carbon-based chemistry. That being said, some have hypothesized perhaps extraterrestrials, so living things from other planets, might potentially be something like silicon-based life forms, and silicon is right below carbon in the periodic table, so also a tetravalent molecule, a little bit heavier, which may make it a little bit more cumbersome in terms of its ability to create the kind of diverse molecules that we see with carbon, and perhaps that's why carbon was in fact the choice here on Earth from a chemical standpoint, from an evolutionary standpoint. But some sci-fi writers have suggested perhaps silicon could work, and from a chemistry standpoint, it's possible. When we look at carbon in terms of its structure, it is very often paired with at least hydrogen. Oxygen and nitrogen also play a major role in organic molecules as well. If you've come across these particular shapes in chemistry before, this is just some of the idea as to why carbon probably makes a really great molecule for building the diverse compounds that we see. When we talk about carbon making 4 single bonds, we talk about this tetrahedron structure, something like methane here, and it really does set up those bond angles to be at this maximum amount of distance from each other. So remember that in each of those molecules, we've got to be able to space out those electron negative charges as far as possible. And so when we get into a tetrahedron structure like that, each bond angle is 109.5 degrees from each other, really maximizing that distance as much as possible. We constrain that a little bit when we start talking about other structures. If we look at a trigonal planar situation, something like ethene down here, our bond angle gets a little bigger. We get 120 degrees Celsius, or excuse me, 120 degrees from each other. Ethane here is a little different. While we're on this idea, this is an interesting thing when we look at the connection between carbon molecules. We'll talk about something called isomers in a little bit, and this is going to become an interesting player. So if I've got a carbon-to-carbon single bond here, these molecules can actually rotate around that single bond, and so I can get this guy to spin on either side. And so there's a lot of flexibility in the way that that molecule works, fits into different structures inside a cell or something like that. I add a double bond here, and now I've created a rigid structure so that these carbons aren't able to spin. And that also then sets up some interesting dynamics when we start talking about things like isomers. So carbon skeletons really form the backbone to carbon chemistry and life molecules, organic molecules as a result. And these carbon skeletons really are just looking at the number of carbons, how do they get put together, how many branches are there, are they double bonds, single bonds, potentially even triple bonds, although those triple bonds aren't super common in living molecules, or they are actually capable of bending back on the rings. So if we look at something like this, those prefixes actually mean something in terms of telling you how long they are. So meth, which isn't here, but you see it back here, meth means a single carbon. Eth means 2 carbons. Pro means 3 carbons. And then you get up to things like hex and sept and pent, which are maybe some other prefixes you've come across in places like geometry class, where they may be a little more familiar to you. Bute here is 4, all right? And then we can start adding on branches. So if we look at something like 2-methylpropane, now I know that it's still 4 carbons, right? Okay, but I have a methyl group, which is a CH3, coming off the second carbon, hence the 2. And so I can use this naming convention. So second carbon, methyl group, and then there's 3 in the major chain, so 2-methylpropane. That's one naming convention. Another way you may come across the same compound is to call it isobutane. So again, butane meaning that 4 carbons total, and then the iso meaning that there's a branch. We can also talk about double bonds, and we can name where they occur as well. So if you've got an ANE ending, by the way, that means they're all single bonds. ENE means there's a double bond somewhere, and then we can number them. So 1-butene is that double bond is connected to that first carbon. All right, 2-butene means it's coming off the second carbon. 3 would be coming off, so on and so forth. And then if we put the cyclo in front of it, it's a ring structure. Again, cyclohexane, all single bonds. That's what the ANE tells me, and then cyclo tells me it's a circle, and then the hex tells me how many carbons. Benzene's a pretty common one that shows up in a lot of carbon chemistry, and benzene is in and of itself an interesting one. So it is a 6-member carbon ring, but every other carbon has a double bond. And so what becomes really interesting about benzene rings is that they're incredibly stable. And the reason for that is because those double bonds can actually flip. And so they can rotate inside here. And so you may also see a benzene ring where you've got the same basic structure, but instead of drawing those double bonds in there, they just put a circle in the middle. And that's really because those rings can flip around. And so in any given point in time, it would be very difficult to distinguish where exactly that double bond structure is because they just constantly rotate. So the absolute basic structure to an organic molecule is a hydrocarbon. And hydrocarbons are the basic principle behind organic chemistry in the sense that they only contain carbon and hydrogen. They're not super prevalent in living things, at least not by themselves, but there are certainly plenty of molecules that have regions of hydrocarbons. Fatty acids, for example, and things like fats and phospholipids, triglycerides, those all have fatty acid tails. And so those tails are in and of themselves hydrocarbons, but they're connected to something else. The big classification, big characteristic of hydrocarbons is the fact that they are nonpolar. And as a result of being nonpolar, that makes them hydrophobic. So they don't really like to interact with water very much. In fact, they'll kind of form these droplets or these spheres in water as a result of the fact that they're repelling the polarity of water itself. Hydrocarbons, however, when they undergo reactions, release relatively large amounts of energy. So when we talk about the difference between your body being able to burn fat molecules versus something like glucose, you get a hugely large increase in the amount of energy that burns when you burn a fat molecule. It's also why they make incredibly great fuel sources. So when we look at propane or gasoline, they're all big hydrocarbon molecules that are really good at creating energy as fuel sources. So I mentioned to you when we first looked at that basic structure for carbon molecules and mentioned this term isomer. And this is going to be kind of an interesting thing when we look at the structural components of the way organic molecules work in your body. So what is an isomer? Well, it's one of several organic compounds that's going to have the same molecular formula, but the way that in which we put those atoms together is different. So the actual arrangement of the molecule is different. I think the easiest ones to see are the structural isomers, where they've got the same molecular formula, but the arrangement of their covalent bonds and the structure of the carbon backbone is different. So something like having a straight-trained carbon here, right? If I count, I've got 1, 2, 3, 4, 5. So this is pentane. Same number of carbons, 5 carbons, and then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So it would be C5H12. If I come over and look at this one, I still have 5 carbons, count the hydrogens up, it's still C5H12, but the structural arrangement of this is different. So we would talk about this as isopentane as opposed to just pentane because I've got that branch that's coming off. Geometric isomers happen on, again, same molecular formula, but now I'm talking about different spatial arrangements, and these happen very commonly around carbon-to-carbon double bonds. So I can get a cis isomer where I've got my double bonded carbon and the functional group that's coming off of that double bonded carbon is on the same side of that double bonded carbon. So remember, these guys can't spin. I'm stuck in this plane, and so I can't rotate. And so those cis isomers have this group on the same side. If I look at a trans isomer, they are transverse from each other, or they're on opposite ends of that carbon-to-carbon double bond. So cis is on the same side, trans is on the opposite. And that does have a role in the way that those molecules are able to plug into things like cellular receptors to send messages, because the structure truly is different. And because I can't rotate around that double bond, I can't change the orientation to get those X's in this case, or these two groups to be on the same side. We're stuck where they're at when they're built. Anti-isomers are probably the hardest ones for kids to recognize. These are actually mirror images of each other, and so they actually talk about them as left-handed versus right-handed molecules. And these are common when we look at asymmetrical carbon molecules, right? These trigger, these sort of, I've got carbon in the center, I've got 4 groups coming off of them, but each of those groups is different. So asymmetrical, right? And the reason they talk about them as left versus right-handed is because no matter how I spin it, I can't ever get the groups to line up identically. The orientation of them rotates, and it's like your palm, right? You can get your palms where you've got both palm sides up or both palm sides down, but if you look at your fingers, right, the orientation of them is different. And even if you were to flip one hand to get your thumbs on the same side, pointing in the same direction, now you've got a palm up and a palm down. So they're never identical to each other in every way, shape, and form. And that's really important, especially when we talk about pharmaceuticals, because a lot of molecules that we create, if we're not careful about how we do it when we're creating them in a test tube in a lab, we often end up creating these anti-isomers of molecules. So one ends up being biologically active and functional, and oftentimes the other antimer is inactive and sometimes even becomes a problem. And so we have to be very careful with that. So when we look at something like the ibuprofen here in the diagram, in the table, right, it's used for pain, it's inflammation, it's what maybe some of you guys know as Advil. And the S form is active in our bodies, the R form doesn't do anything. So one-handed version works, the other one doesn't, and it's because of the way that it orients itself into the pain receptors in our cells. Albuterol, which is used for asthma inhalers, same idea. The R form is functional, the S form is not. If you take a look at your textbook, they talk about the L-DOPA drug and the use on Parkinson's disease. And again, one form functions in the body and the other one does not.
On October 1st, 1957, a new over-the-counter drug was introduced in West Germany that was supposed to basically cure morning sickness during pregnancy. It was called thalidomide. Thousands of women purchased the drug and were relieved when their morning sickness disappeared. And everything seemed great until later the next year, when thousands of infants were born with severe birth defects, like brain damage and deformed limbs. Doctors noticed the surge, but at first they couldn't figure out what was causing it. Then, 2 doctors, Wiedekind Lenz from Germany and William McBride from Australia, both noticed that the mothers of these babies had all taken that amazing new morning sickness drug. By 1961, Lentz had proven the link between thalidomide and the birth defects, and it was pulled from the shelves. But by then, thousands of infants had been born with those birth defects, and nearly 40% of them had passed away. Rules for drug testing weren't as strict back then, and in this case that cost thousands of lives. Even though they were now aware that thalidomide was a problem, scientists still didn't know why. It turns out the answer lies in its chemistry, or more specifically, its geometry. What researchers didn't know at the time was that there were actually two versions of the thalidomide molecule. Thalidomide, which is made up of 3 connected rings of carbon and nitrogen atoms, plus some oxygen and hydrogen, is what's known as a chiral molecule. Chiral comes from the Greek for hand or claw, and chemists often think of chiral molecules as being right-handed or left-handed. And that's because the different versions of chiral molecules, called enantiomers, are made up of all the same parts but arranged differently, just like your hands. If you try overlaying your right hand on your left, you'll see that no matter which way you turn your hands, you can't make them match up. Even if you make your thumbs line up, one hand is palm up and the other is palm down. In other words, both hands have the same 5 fingers, but they're not identical. And molecules like thalidomide are the same way. A chiral molecule has an atom, typically carbon, with 4 different groups attached to it. That's called the chiral center. A group can be anything from a single atom to a long chain to rings. In some cases, 2 groups can even be connected. These groups are kind of like your fingers. In each enantiomer, the groups are attached to the chiral center in the opposite order, so they're mirror images of each other. In thalidomide, for example, the chiral center is a carbon atom attached to one of the rings. It's bonded to 2 other carbons, a nitrogen and a hydrogen. If you position the version of the molecule that's considered right-handed, called the R enantiomer, so the closest oxygen atom to the chiral center is below it, the hydrogen atom attached to the center will be facing away from you. But if you position the left-handed or S enantiomer the same way, the hydrogen atom will be facing toward you. In other words, the 2 enantiomers are mirror images of each other. And because different receptors and enzymes in your body react with molecules in very specific ways, the fact that enantiomers are mirror images means that they might react to things totally differently. In the case of thalidomide, scientists discovered that the R enantiomer helped with morning sickness, but the S enantiomer caused those severe birth defects. One of the most famous, or maybe infamous, examples of how 2 enantiomers affect the human body is methamphetamine. You'd probably associate that name with the street drug, but the molecule can only really break bad when it's in its R formation. The S enantiomer is commonly sold over the counter as a vasodilator, and you can easily find it in vapor inhalers. But the vapor inhaler you just bought at the pharmacy isn't filled with a dangerous drug, because the S version will never be psychoactive. After researchers discovered that only the S version of thalidomide caused birth defects, they thought about isolating the R enantiomer so they could continue to use it to treat morning sickness. But it turns out that thalidomide's R enantiomer can actually switch to the S version while inside the human body, meaning that even if they'd isolated 100% pure R thalidomide, it still wouldn't be safe for pregnant women. But in 1998, the FDA did approve thalidomide, almost 40 years after rejecting it based on the birth defect problems. This time, though, it was approved for treating complications from Hansen's disease, aka leprosy. And recent research is also leading some scientists to believe that in certain cases, thalidomide could help with a number of debilitating diseases, including some forms of breast cancer. They just make sure not to prescribe it to anyone who's pregnant. Thanks for watching this episode of SciShow, which was brought to you by our patrons on Patreon. If you want to help support the show, you can go to patreon.com/scishow. And don't forget to go to youtube.com/scishow and subscribe.